Welcome to the Yaka Digital Network. If you tell a traveler to walk 10 kilometers, you've given them a distance, but they still don't know where to go. That measurement is a scalar, a quantity that only has a size or magnitude. To get them to their actual destination, you have to add a specific direction, say 10 kilometers north, towards Gulu. When you combine that size with a direction, you have a vector. Adding that direction transforms a basic measurement into a precise set of mathematical instructions for navigation. To write these movements down mathematically, we use column vectors. We stack two numbers, an x value for horizontal movement and a y value underneath it for vertical movement. Look at this path across a school field. Walking 3 units right and 4 units up is written as the column vector 3/4. But beware, a vector must be a directed line segment. The arrowhead showing movement makes it a vector. Column vectors are the exact mechanism we use to translate a physical path on the ground into algebraic numbers on a page. Looking at our vector on the grid, how do we find its exact physical length or magnitude? Since our horizontal and vertical movements create a right-angled triangle, we use Pythagoras' theorem. We take our x component, 3, and square it. We take our y component, 4, and square it, add them together to get 25, and take the square root. The length of this vector is exactly 5 units. Because magnitude measures a physical distance in the real world, the result of this calculation is strictly positive. A length can never be negative. Calculating magnitude distills complex, two-dimensional movement back into a single, understandable number. When calculating a multi-leg journey, like a boda navigating a city grid, we want to find the net displacement. That is, the most direct path from the starting point to the final destination. To find it geometrically, we use the triangle rule. By placing the tail of the second vector at the head of the first, we can draw a brand new line bridging the start of our journey directly to the end. You don't always have to draw this on a map. Look at the column notation. If you add the top x values and the bottom y values of your vectors, the math directly produces the coordinates of that new path, 5 units east, 3 units north. You must pay attention to the order of travel. Traveling from point A to point B gives you one vector, but going the other way, from B back to A, requires you to flip the mathematical signs. Reversing your physical direction reverses the signs in your math. Vector addition gives us the power to predict the most efficient route without having to travel the long way around. Let's put this into practice. Imagine a boat trying to cross straight over a river while a strong current is simultaneously pushing it downstream. The boat's engine provides a velocity of 3 units horizontal, 0 vertical. The river's current is 0 horizontal, 4 units down. Pause the video now. Add these two vectors together and calculate the true final magnitude of the boat's path. In nature, multiple invisible forces are always acting upon us at once, and we need vector math to uncover our true trajectory. Here's the solution. Adding the boat's vector and the current's vector pulls the boat along a diagonal path, represented by the column vector 3/4. Using Pythagoras' theorem, we find the true speed of the boat along that diagonal is 5 units. By mastering vector addition, we can safely navigate and control our movement, even when outside forces push against us. Let's review. A vector requires both a magnitude and a direction. We write them in column form to track horizontal and vertical changes, and we calculate their physical length using Pythagoras to get a strictly positive magnitude. You can watch more videos for all classes here, and get all content at www.yaka.cc. Vectors give us the exact mathematical language to map our world. They are the tool we use to turn basic geometry into dynamic, real-world motion.